Okay. So, how did people make these measurements of failure, stress amplitude and the number of cycles to failure? What are the ways that we can actually do these measurements experimentally, right? So, as we have said, August Wheeler did the experiments on a rotating cantilever beam with bending. However, most of the data that we are having today, this is not a fully reversed loading. Please keep that in mind, because it may not actually give you pure bending. Okay? So, rotating cantilever beam with fully reversed loading, but it is not, although he says that it is bending, it is not necessarily pure bending. So, it is not really a one dimensional state of stress. Here we are talking, however, the most of the data that we have in the literature is generated due to another experiment, the improvised experiments from Wheeler experiment called R.R. Moore's rotating beam bending test, or rotating simply supported beam. Instead of cantilever beam that Wheeler used, Moore proposed rotating simply supported beam with fully reversed loading, fully reversed pure bending. So, he is managed to get a scenario where you can actually subject the material to pure bending. That means it is only normal state of stress. There are no other stresses in the material. As a result, you actually have a one dimensional state of stress. That is very important, right? Because you remember when we have studied static failure theories, the yield strength of the material we have actually calculated for a material using tensile test, for uniaxial tensile test, and that is the material property that we have used even when you are dealing with multi-axial loading, right. So, here similarly in the case of fatigue failure, R.R. Moore's rotating beam bending test ensures that there is a pure bending, fully reversible pure bending applied. And in literature we have a lot of data available for rotating beam in fully reversible bending. The fully reversible bending test is one of the popular tests and reasonably easier tests compared to other tests. There is, compared to rotating beam bending data, we have less data for axial loading. That means when we are saying rotating beam bending, you actually take a beam and you do apply pure moment and both positive negative. That means what does it mean? You are actually bending this way and unbending that way. That means you imagine when you are bending this way, so you have a component and it bent like that, and in the next cycle this is actually bent like this, right. So, this material point now is experiencing tension and the same material point is now experiencing compression. This is what we mean by time varying load, right. The material is changing its state of stress, nature of stress at the same point from tension to compression. That is what we have plotted in the time varying stress state in the previous slides. Okay. So, you can create pure bending, repeated loading, cyclic loading. Similarly, you can also do an axial test, right, uniaxial tension push pull tests, that is also repeating. So, you can have a fully reversed one. So, that means tension, compression, tension, compression, that is also cyclic. There is that kind of an experiment is not so easy, and then there is less data actually is available for such an experiment, and much less data, there is not so much of data available for torsion. So, you can apply torsional load also cyclic, but the amount of data available for this axial loading and torsional loading is much less compared to pure bending load. And sometimes for certain scenarios the fatigue strength information is simply not available, for certain materials it is not available, or for certain loading scenarios it is not available, then you need to estimate this when the fatigue strength information itself is not available to us. How do we go about doing this estimation is something that we will look at. Alright. So, this is the a schematic that shows how a rotating beam bending test setup look like, and the setup is prepared in such a way that there is the beam experiences pure bending. That means only bending stresses, the normal stresses prevail in the material, there are no other stresses, so as to give a one dimensional loading scenario. So, the no axial stresses are developed due to the vertical load. That is how the test setup is prepared. Please read Norton's textbook on understanding this rotating beam bending test in more detail. Here I am showing you a video in which you will see how this test is done. Okay. So, this is that I have taken from this particular website in Belgium. So, here you see that this top here that guy is pushed, as a result the beam is bent and it is rotating. While it is rotating, you are applying this load, right. So, the material is experiencing repeated loading at a given material point. So, that is how typically a rotating beam bending test is done. All right. So, here I am showing an experimental data on wrought steel, which actually show, when we are talking about steel, it actually shows an endurance limit. Okay. And here what I have plotted on the y axis is S by SUT. I have normalized my stress amplitude. S is not stress, but please keep that in mind, it is stress amplitude. The stress amplitude is normalized with ultimate strength. So, if you see the Ascent diagram, here it should start as SUT. So, that is where it starts, and let us not focus on these lines now, just focus on the data points shown in the white circles. On the y axis you have number of cycles, y axis stress amplitude, both are on log scale. Okay. It is only a schematic. I have looked at the data, experimental data, I have prepared the schematic from the experimental data. So, it is the data points are more or less taken from the real experiments, all right, from the literature. Okay. So, now if you look at this, very interesting scenario happens. For instance, these are all the specimens of wrought steel whose ultimate strength is about 1400 MPa. Okay. And they are all specimens from the same batch. Each specimen is different, but they are from the same batch. And you would expect, normally if you would do a tensile strength, you would expect a small variation in the properties that you would measure, but the variation is not expected to be very high if all the specimens are cut from the same batch. Okay. Here all the specimens are cut from the same batch. However, if you see a specimen, so for instance you take this sample, both of them are subjected to same stress amplitude, say something like 0.75, normalized stress amplitude to be 0.75 SUT, normal stress amplitude. But this specimen gave a life of say 2 into 10 power 4 cycles, whereas this guy has given say 5 into 10 power 4 cycles. Okay. So, the number of cycles, the life that it is giving are different, the same specimen, but the number of cycles failure is very different from one guy to another guy, although both of them are subjected to same stress amplitude. Okay. And you see that here it is subjected to a higher stress amplitude. Now, you look at this point, it is actually subjected to a lower stress amplitude. Then what you would expect? You would expect a higher life, right. We do not expect this guy to be here, you would have expected this guy to be somewhere here, because the stress amplitude is less, but here it is showing premature failure. While there is at the same stress amplitude, the other guy is showing a higher life, number of cycles. That means what we are saying here, now if you would look at these guys, it is very difficult to say anything conclusively about the behavior. However, these data points nicely fall under these two bands of the brown line and the red line. And there is lot of noise in the data, that means there is lot of standard deviation for the data, and this is typical of several fatigue experiments, any fatigue experiment. Why is that? As we have discussed, the fatigue failure has three different scenarios, right, the three different stages: crack initiation, propagation and final failure. The crack initiation stage depends on the internal microstructure of the component. Although the microstructure is the same, but the micro crack structure that is prevailing in the specimen 1 and specimen 2 is not necessarily be the same, right. So, your micro crack distribution could be very different from one specimen to another specimen, and because of the fact that the micro crack positioning or distribution is very different, the position where this micro crack is there may be subjected to a higher stress in specimen 1, and in the other guy it may be subjected to a lower stress. As a result, both of them are giving you completely different lives. However, but if you see a big picture, you would see that general trend is this way, and that is what people have observed, and they said that you have a lot of scatter, nevertheless you are able to put them under a band, and then you could have given a nice expression, a mathematical expression to represent this guy. Okay. However, and you can see that here I have shown some green circles here, these samples never failed. For this wrought steel, they never failed, beyond 10 power 6 cycles they never failed, and that is precisely what we said endurance limit, right. The material will not fail below certain stress amplitude, for instance this guy, right, below certain stress amplitude they never fail, and that is what we call endurance limit of the material. Okay. So, this endurance limit is typically taken as 0.5 times SUT, that is SE dash endurance limit is taken as typically 0.5 times SUT. Okay. So, this is how your typical experimental data for a specimen subjected to fully reversed loading, bending load looks like. So, for steels the endurance limit is taken as 0.5 times SUT if ultimate tensile strength is less than or equal to 1400 MPa. Otherwise, if the ultimate tensile strength happens to be greater than 1400 MPa, you take SC dash is equal to 700 MPa. That is a general guideline. Okay. So, as we have discussed, this is the data given for the wrought steel with 200 pounds per square inch or 1400 MPa, and the test is run at a particular stress level until the given specimen fails. The test is repeated at another stress level using different specimen of the same material. Samples run at higher stress levels fail after fewer cycles. At lower stress levels, some do not fail at all, not broken data, until the test is stopped. It is not broken until the test is stopped. So, a test here is stopped at 10 power 7 cycles. The scatter in the data is probably due to unknown defects of different sizes in different samples, as I have already discussed. So, how does the SN diagram look like for different materials? The SN diagram on normal linear scale looks something like this. This is for ferrous materials which show endurance limit. This is for non-ferrous materials which do not show endurance limit. So, it is a power law kind of a relation that you would have. Okay. Only when you plot that in a log scale, then you would see it as a straight line almost. So, for SN curve for aluminum alloys which are non-ferrous, they do not show a knee. What do we mean by knee? Something this, you don't see a knee showing, meaning there is no endurance limit for these materials. When we are talking about aluminum, we should not talk about endurance limit. What we should rather talk about is something called fatigue strength. So, fatigue strength is denoted by SF dash and endurance limit is denoted by SC dash. So, instead of using SC dash, you should use SF dash for aluminum alloys. And you can see that the slope of these guys start to decrease at 10 power 7 cycles, beyond 10 power 7 cycles. So, the fatigue strength of aluminum alloys, because they do not have an endurance limit, you define something called fatigue strength. How do we define the fatigue strength of aluminum alloys? The fatigue strength of aluminum alloy is defined at 5E8 cycles. Fatigue strength of steel, so endurance limit of steel is defined at 1 million cycles. At 1 million cycles, what is the stress that it gives? That is 0.5 SUT. That is your SC dash endurance limit. Whereas for aluminum alloys, you look at 5E8 cycles. So, as SF dash at 5-8 cycles is usually 0.4 SUT for aluminum alloys, for SUT less than 48. But if it is SUT is the SUT is your ultimate tensile strength. If it is greater than or equal to 48, you will take it as a 19 KSI. That comes out to be this one for this guy. So, you will not increase your SF prime beyond 0.4 SUT or 19 KSI. All right. So, that is about rotating beam bending. What happens in an axial fatigue test? So, let us compare the fatigue failure lines on a log-log scale for a rotating bending test and a push-pull test, that is axial test, done on a SAE 1090 steel. You see that rotating beam bending test is this and push-pull test is this. What is the meaning of that? Suppose if you take same a particular stress amplitude, if you are subjecting this guy to a particular stress amplitude, a push-pull test gives me this much life, whereas if the material is subjected to beam bending, fully reversed bending, and as opposed to fully reversed axial load, the fully reversed bending scenario gives me longer life compared to push-pull test. Why is that? Why does that happen? If you take a shaft, okay, subjected to axial loading, push-pull test, the same shaft bending, this is axial loading and this is bending, right. Now, if you look at the stress state from the if you look at the stress state through the thickness, let us assume that this is a solid shaft, okay, then in this case the stress state at the neutral axis is 0 and the outer layer is maximum, right. That is how the stress state changes, and this is our 0, sorry, and that is my sigma max, that is for bending. And now let me plot it for the same, because sigma amplitude is same, so the magnitude will be the same, and this is my neutral the central line axis, and the stress state is going to be, because this part is tension and that part is compression, and here the stress state is going to be same everywhere because the entire cross section is subjected to axial loading. So, you can clearly see in the case of axial loading, there are more material subjected to a larger amount of stress compared to pure bending scenario. That means, imagine you have a crack network, micro crack network, there are more micro cracks that are prone to experience higher state of stress compared to the beam bending test, and that is the reason why this is much more severe compared to beam bending scenario. That is why for the same stress amplitude, your axial loading will give a lower life compared to rotating beam bending test. Okay? So, that means axial fatigue is actually going to be more severe than pure bending fatigue, keep that in mind. Okay? So, there are also other fatigue testing methods possible, that is cantilever, which is the first test the Wohler, August Wohler did, right, and you also have a torsional test, but these are torsional test is little bit more complicated to do, but you can find the data of these tests in the design data handbooks. Alright, so now let us look at the schematic of your SN diagram in LCF as well as HCF regime. So, what do we mean by LCF regime? LCF is nothing but 10 power 3 cycles, less than 10 power 3 cycles, HCF is beyond 10 power 3 cycles. So, here if you, so this here I am plotting 1E0, 1E2, 1E4, 1E6, right. So, here you have S by SUT, this is 1, so this is actually SUT, and here it is 0.9, 0.8, 0.7, 0.6, 0.5. So, in the LCF regime you have one line and it ends at 0.9 SUT. Okay, and this is your 10 power 3 cycles, because this is 10 power 2 and this is your 10 power 3. Okay, 10 power 3 cycles, 2E3, 2, 3, 4, 5, so this is 1000, 2000, 3000, 4000, 5000, 6000, 7000, 8000, 9000, 10,000. This is your 10,000 cycles. Okay, at 1000 cycles you have 0.9 SUT, and at 1 million cycles you have 0.5 SUT, that is SE prime by SE dash by SUT, and this one what we call SM. At 0.9 SUT, SM is equal to 0.9 SUT, and SE dash is equal to 0.5 SUT, and that is the line that you will join. And normally on a log plot, on a normal plot, it will be like this, right? So this is our SN. So now you can actually represent that as S is equal to AN power B. That is a power law. A and B are your material constants. Okay, but here it looks like when you take log on both sides, you will see that it is a straight line, right? Because if you take log S is equal to log A plus B log N, isn't it? And as a result, you have this is log S if it is Y, and this is a constant C, and this log N is X and B is slope. This is a straight line, right? Y is equal to mx plus C is a straight line equation in log scale. That is why it is a straight line here. It can be approximated that way. All right. So the region left to 10 power 3 cycles is called LCF regime. The region right to 10 power 3 cycles is called HCF regime. Okay. So we are going to focus our attention to HCF regime only. We are not going to do any analysis for low cycle fatigue regime. So that is your LCF, and that is your HCF regime, and that is your endurance limit. So this part is LCF and that part is your HCF. Okay. All right. So now let us do this exercise and then be able to understand how to construct an estimated SN diagram. So create an estimated SN diagram for a steel bar and define its equations. How many cycles of life can be expected if the alternating stress? So alternating stress is also having, this is another name for stress amplitude. Alternating stress also means stress amplitude. Alternating stress is 100 MPa and 400 MPa. What happens? How many cycles of life can be expected if the alternating stress is 100 MPa? How many cycles of life can be expected if the alternating stress is 400 MPa? The ultimate strength of the material is 600 MPa. Estimated strength at 10 power 3 cycles is 0.9 SUT. Why is it required? If it is not given, then you assume it to be 0.9 SUT. Okay. So you have the system where you have SUT is equal to 600 MPa. When you are drawing your SN diagram at 10 power 3 cycles, it is at 1 cycle it is SUT, but at 10 power 3 cycles it is 0.9 SUT. That is SM is equal to 0.9 SUT, that is equal to 540 MPa, right? This is our 540 MPa. And then SE dash, so this corresponds to 10 power 3 cycles. SE dash is equal to 0.5 SUT, but at 10 power 6 cycles. That is important. You need to know 2 points in order to draw a straight line. So 0.5 SUT is about 300 MPa at 10 power 6 cycles. So this is a log plot. Let us say this is my 10 power 6 cycles and this is my 300 MPa, right? So that is the second point. Then you draw that line, and that is my SN diagram. And after that 10 power 6 cycles it is supposed to be, because it is a steel, that is what it should be. Okay. So we know this guy is represented by S is equal to AN power B, correct? So you can write log E S is equal to correct. So, now you can use log E or log 10 because here 10 cube is there. So, let us use log 10, does not matter, right, and then you write so this is the first point is 540, sorry not 540, x is 10 cube 540 and this one is 10 power 6 300. By substituting 10 power 3 540 and 10 power 6 300, we can find A and B. Then you can write our S is equal to A n power B is the failure diagram for this material, right. So, you would have found what is your stress life diagram. So, this is the equation that we need to figure out. Okay. So, here is SUT and this is SM, that is 540 and this is 300 is your SC dash, right. And now what we are saying is SM is equal to 0.9 SUT, SM is equal to 0.75 SUT. Now what he asked you is what is the number of cycles, how many number of cycles of life can be expected if the stress amplitude is 100 MPa, and you see that here if the stress amplitude is 100 MPa which is below the endurance limit and hence this should be safe. But if the stress amplitude is 400 MPa, it is actually above the endurance limit. This is 400 MPa, that means this is the failure life, that should be our. So, you should be able to find out how many number of cycles it will give. So, that means how will we be able to find out S is equal to A n power B? Only when you know A and B, by plugging in S you will be able to calculate n, right, corresponding to S equal to 400. So, to do that we have actually used these two boundary conditions to find the values of A and B, because that is the material properties for that particular material. And then if you know, let us say 400, what will be, let us say this 400, what will be this, by plugging in using this equation you will be able to figure out how many number of cycles that the component will last. Okay. So, you can actually find out, I am not going to show you how to what is the value, but I would expect you to find out by looking at the figure graphically. If you have drawn this guy without actually solving any equation, you will be able to predict this graphically, but by writing the equation you can also predict the value exactly. Okay. And please note that here I have used something called no correction factors. That means I have not used any correction factors in estimating these values, right. So, where does this term correction factor come in? The reason why we need to be using correction factors is because the estimated SN diagram, this is what we call an estimated SN diagram, where if you know the ultimate strength of the material, if it is steel, then if I know the ultimate strength of the material, then I can take this point as 0.9 SUT and this point as my 0.5 SUT corresponding to 10 power 6 cycles, and this is 10 power 3 cycles, and then I will be able to calculate my A and B in the equation S is equal to A n power B. I can find out my A and B are the material properties. But this SM corresponding to 0.9 SUT, SE dash corresponding to 0.5 SUT at 10 power 6 cycles is based on the experimental conditions proposed by R.R. Moore's rotating beam bending test. What are those conditions? For instance, the R.R. Moore's rotating beam bending test is done for a specimen of a certain size. It is done on a circular cross section of diameter say 8 mm. But if your real component is not of the same size, then your defect concentration is going to be very different, right, and hence you need to account for this change in size. As long as the size is less than or equal to 8 mm, you do not have to worry about that size variation, because these numbers have come in due to that size of the rotating beam bending test. If you are dealing with a different size, you need to take into account of the variation in this size. And again, the experiment was done at room temperature. But what if your component is in the service, the component in service is actually working at a different temperature. So, you need to account for this change in temperature as well, right. Similarly, you know that you have a lot of scatter in the data when you have looked at the rotating beam bending test. So, the reliability of the data is taken to be 50%, but when you are doing the design calculations, if you want to have higher reliability, you need to add some correction factor to that as well, and so on. So, that means if your component being designed is going to be different from the rotating beam bending test based on which we have constructed the SN diagram, then you need to account for these changes through correction factors, and that is something that we will look at in the next class, that is about correction factors. And here we have not used any correction factors, but we will look at the same problem when you apply the correction factors, and then we will see whether this 100 MPa will still be under safe or it is going to be unsafe. So, when you are changing these correction factors, your endurance strength is going to change. That is what we are going to look at in the next class. With that, I stop here today, and thank you very much for your attention.